Why is the divergence equal to 0? Well, because you're going to be doing a dot. What's the very first part of the dot product you're going to do? Yeah, right? Again, you know, let me write it out. I think it's important to see this, right? So quick check 1. When we say div f, that means this operator dot f, right? Well, the operator is this. Partial with respect to x, partial with respect to y, partial with respect to z. Dot, what did they say f was? The important point was they said f is a function of y and z, right? G is a function of x and z. And if that happens, and h is a function of x and y, right? So what happens is if you take the partial with respect to x of some function that doesn't have any x's in it, you treat all that as a constant, you get 0. Plus 0 plus 0 is 0. Okay. Let's go to quick check 2. Love hints. I always use hints, right? So let's see. I'm going to write that down. We have f dy minus g dx. Okay? And it says, hint, if you try this and you want to use Green's theorem, convert to polar coordinates. Now, I need to look at example 3 a little bit because I don't have it in front of me. So let's get it. Is that this picture up here? Yep. Divergence from the graph. So they're talking about Q11, okay? And so my f here, it says is x squared comma y, right? And so on my paper, I guess I should point that out. Little f is x squared and little g is y, right? So that's important to understand. Okay. And they say, hey, if you want to use Green's theorem here, what does Green's now, I guess, do we have a closed curve? I better check. They tell me it's a circle? Oh, yeah, circle of radius 2 centered at the origin. Okay, so we really do have this situation. C is a circle of radius 2. Can we parameterize it? How? How would you parameterize a circle of radius 2? Well, we know that, yeah, I mean, we like to say that, yeah, I mean, what, 2 cosine theta plus 2 sine theta? Maybe I'll use t. Everyone okay with that? That's r of t. That's a clockwise orientation, right? T just has to go between 0 and 2 pi. Right? So you could, I guess we could do it directly using this parameterization. That's one thing we could do. But they say, hey, what about Green's theorem? All right, I'll try Green's theorem. So by Green's theorem, with the green marker, just for kicks, this equals the double integral, right, over that region R, okay, of f dot n, right? So, hang on.
How do you know which way to go on Green's theorem? Whether you go that way or you go back the double integral of the partial of f with respect to x plus the partial of g with respect to y?
So df dx plus dg dy dA. Maybe that's easier just because I already wrote down what f and g are, right? Okay. So let's think about that. Let's think about that. So if we want to write it that way, right? So we're going to do an iterated integral, and it would be 2x plus 1, right? And since they said to use polar coordinates,
Yeah, that's why I just stopped.
you did?
I was like, why? It looked like I did something wrong because like there's no more y's, it's polar coordinates.
Well, we have an x, right?
Yeah.
So what are we going to do with the x?
R cosine theta.
Yeah. So let's take their hint. I like taking hints. So let's write this as 2 times, now r cosine theta, right, is what x is. So we'll write it as 2r cosine theta plus 1 times r dr d theta.
Did you change that to t or not? Did you use t in your parameterization?
Well, again, I was thinking about parameterizations if I'm going to go directly here without Green's theorem, okay? Or if we're going to be doing it as a vector field, you might need it also. But let's do this. This must be what they meant by the hint, right? So theta, well, we know that's going from 0 to 2 pi, right? Now r, we should be able to write as a function of theta, right? Oh, but it's a circle. So the region that's really simple, right? 0 to 2. Yeah, I could see why they wanted polar coordinates. Well, it makes sense. Anytime my region is circular, I'm going to save a lot of headaches if I go polar coordinates. Okay. So now, what are we going to do first? Integrate r or theta? I guess may as well do r. So integral 0 to 2 pi, integral 0 to 2. Let me write this as 2r squared cosine theta plus r. And then we'll integrate dr and we'll integrate d theta. So when I integrate dr, let me leave the 0 to 2 pi here. And let's see, this becomes 2/3 r cubed cosine theta plus 1/2 r squared, right? And we're going from 0 to 2. And then we'll integrate d theta. And so moving up here, this equals, well, if I plug a 2 in, do I get 16/3 cosine theta plus 2? Does that look right to you guys? You are checking my math, I hope? Am I going too quickly? Am I going too slowly? You're going just right. Okay, so here we go. When we integrate d theta, right, we get negative 16/3 sine theta plus 2 theta from 0 to 2 pi. I love when I'm going from 0 to 2 pi and I have a trig function, because this, whatever it equals, is going to cancel out when you plug in a 2 pi and a 0. Matthew?
I know it's gonna cancel out, but shouldn't it be positive 16 over 3?
Yep. I agree. Because the derivative of sine is cosine. And so I get 4 pi. How's that sound?
So because that comes out to be a positive value, that's proving that that net flux is positive.
Right.
Right? Okay.
Right.
Which means more is going out than is coming in.
That's right. The outward flux is 4 pi, so it's positive here. Okay? Hey guys, what's coming? 3-dimensional. Across the surface is the flux positive. Same deal, guys. It's just a generalization of what we just did, but it's what people really care about. You have a point charge. Will the flux across this surface be inward or, positive or negative? For instance. They'll talk about it in thermodynamics. They'll talk about it in all kinds of stuff I never studied.
All right, so here's a silly question. So if you've got some thing up on a power lines that, one of those, what are those things? Transformers?
Yeah.
You've got a certain amount of power coming in, a certain amount of.
So we're supposed to do, if you have this, the curl is 0. Is this worth showing, or is this one for you guys? It's worth showing. That's what I thought we'd say. QC3. It's funny, I told Carl, I said, you know, it'd be great if you went over these quick checks. I knew there was no chance he was going to do it. All right, so here we go. So quick check 3. Right? We have to compute this. So again, what does that mean? It means we're taking the operator with ddx, ddy, and ddz, and now we're doing a cross product with, and what's our vector field? It was, oh, okay, f of x. So f is only a function of x, g is only a function of y, and h is only a function of z. And so I guess now I'm really tapping into, what did you guys ever learn about cross product? I remember teaching some of that here, that it's really the determinant of a matrix, where what you do is in the top row, do you remember what we put? Yeah. And really, those are the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. Here I'm going to write these little operator symbols, partial with respect to x, partial with respect to y, partial with respect to z. And here I'm going to put f of x, g of y, h of z. Okay? And guys, when you take the determinant of something like this, you know, I like to work right across the top row. Because when I work with I, then I'm just looking at this submatrix, right? So, for example, it's going to be I times what? The partial with respect to y of h of z minus the partial with respect to z of g of y. Right? Minus j, because remember you have to do a minus because it's a checkerboard pattern, times the partial with respect to x of h of z minus the partial with respect to z of f of x. What do you notice about every single one of these parentheses? Why?
Because if you take a partial with respect to y of a function of z, there is no y.
Exactly. And the same thing's going to happen for the last one. And so you really have a lot of zeros, right? So, what is the answer? The answer, let's be very careful, is this, right? The book will boldface your 0. It's the 0 vector, not the 0 scalar. I will penalize severely if you get that wrong. Yeah, if you put a 0 scalar like that on your final, I'll put a 0 scalar as your no, just kidding. Which is worse, a 0 vector for the grade? Anyways. No, work hard at learning to. You'll see, great problem tonight, 41. Does this even make sense? And you'll see these different symbols, and they'll drive you crazy. And drove me crazy. But once you figure them all out, you really start to get a handle on what these things are. The divergence, the curl. Okay, question 4. Where'd it go? Oh, here. Working with divergence and curl. Oh yeah, lots of nice properties. Associative properties and distributive properties and plenty of others. And so now they want me to prove, oh yeah, is grad.uf a vector function or a scalar function? Now let's see what we can do with this. Right? QC4. Grad.uf. Now what is u? Let's be very careful in my notation because I don't have bold-faced. All right. Is it true that u is just some scalar? Seems like it is up here. It's a scalar valued function. So it's kind of like u of t or u of x, right? We've used that before. But f, we know, is one of these vector fields, right? So let's see how that would work. Grad.uf. And then, of course, up above it says it's grad.u.f plus u of grad.f. Okay? So it seems to me, if this is true, it has to be a scalar function. I mean, I'm not working anything out. I'm looking at the blue box, right? It's a scalar valued function. They point out that that's the divergence. Okay, because again, we did grad dot something. When you dot product, you get a scalar. When you cross product, you get a vector. So Kathy, back to your question you asked me a while ago. I said, here's the best way I can answer your question. You say, what is the divergence? How about I just say it's a scalar valued function with what is its input? I mean, what you did was you had a vector field and we get some scalar from it. Let me compare it to something you guys have seen before. I taught it to you guys, even though it's not part of this class particularly. You guys, what's the determinant of that matrix? It's -2. It's 4 minus 6 is -2. What's the determinant of my favorite matrix? It's 0. We did it in class. Actually, that's significant. The fact that it's 0 means this matrix doesn't have an inverse, and it means lots of other things. Come take my course sometime if you want to learn what they are. Okay? The fact that this is non-zero is meaningful. But if someone asks me, what does the determinant really tell you? The best thing I can probably answer is that, hey, you input a matrix, I'll output a scalar. What does it really tell me, Paul? Well, okay, if you're talking vectors, it can give me, actually, you may have learned this, it can actually give me the area of a certain parallel pipette or volume of the parallel pipette from the vectors involved. But I don't go that route particularly. All I want them to know offhand is just understand that the determinant is a number that's associated with a matrix, and it does have meaning. As opposed to when I take two matrices and multiply them together, I get a new matrix sometimes. Okay? Usually, if it's defined. Sometimes it's not defined, that's the problem. Same idea here, guys. When we do grad cross a vector field, right? We're getting a new vector field, right? This is vector valued function. That's kind of the idea. If you know that much, I'm kind of happy. You know, kind of like in Calc 1. Here's f of x. Guys, what's f prime of x? It's a new function. Sometimes we get into trouble when we say it's the slope of a tangent line. No, it's not. It's a function that can help me find the slope of a tangent line anywhere I want. But it's not the slope of the tangent line. So I guess that's how I would close this session. Guys.